The last class had been devoted to the polar decomposition theorem. So I want to notice a couple of special cases of that. Okay, so first consider the special case. Okay, so let me start again. So we wrote x equals v mod x, with v star v equal to the support of mod x. So consider the special case where x is self-adjoint. Then you can see, because you're only talking about functions really on the line, you can see that mod x equals x plus x minus for functions of u, you can see that mod x is exactly x plus x minus, and v is going to be actually equal to support of x plus minus support of x minus. And on x plus, v is going to be plus 1. On the support of x minus, v is going to be minus 1. V is also going to be in the one-dimensional algebra generated by x. In C-star algebra generated by x. Not C-star, one-dimensional. But we haven't yet started talking about one-dimensional algebras. We're getting there. We will be getting to that soon enough. Okay. So notice that in particular this means that V is actually self-adjoint also. Because it's just a difference of projection, so it's self-adjoint. Okay, let me give a little exercise. This shouldn't be hard to prove. X normal implies V mod x equals mod xv. And see, what I'm saying is, if you take the polar decomposition of a normal operator, the two parts will commute. Similarly, in the Cartesian decomposition also, the two parts will commute. If you write a normal operator as x1 plus ix2, because they're both just averages of x and x star, they will also commute. Okay. Okay, so now I want to start talking about positives more seriously. So we will write B of H H.
So is this sufficient condition also? X is normal if and only if?
No. Okay, for you, another exercise. Give me an example of something which is not normal but which satisfies this.
Shift operator will be correct.
Huh?
Shift operator will be very correct. I'm not sure, sir. I have to.
So you have play around with it. In fact, because for this reason there is a separate, they coined a separate name for such operators, things for which the polar and these two parts commute. They are called quasi-normal operators.
But quasi-normal operator has normal extension.
What do you mean normal?
They are subnormal operators. So they have normal.
They are not normal. Quasi-normal does not imply normal.
Subnormal, I'm saying, sir. They are subnormal.
No, they are not. Okay. So this will be the set of self-adjoint elements of BFA. The set of Hermitian elements, right? So we'll write this for this will stand for Hermitian. We'll write B of H plus for the positives. Positive operators. Okay. So two things to note is that if you have two positive elements, what can you say about the product?
Be a positive operator.
To be positive means what? Positive means self-adjoint and the quadratic form is positive. Why is this self-adjoint? What is the adjoint of AB? Huh? BA. So, if A and B commute, if and only if actually. And if A is positive and X arbitrary, and this will be easy to see because you just, this clearly self-adjoint, and if you look at the quadratic form, it is really the restriction of the quadratic form of A on something. Or you use the other thing that this is something star something. This is x8 to the half times the adjoint of it itself. Okay. So we'll be using this fact very often, namely that the map sending A to XAX star is a positivity preserving mapping. Okay. All right. So here's a little proposition. Suppose xi ini is a uniformly bounded by that I mean the soup norm is finite. The supremum of norm xi is finite. Monotone increasing net in BFH plus so is it clear what that means? When I say xi is the net, that means this I is already a directed set. It is an ordered set. And to say that the monotone is exactly like saying you have a monotone sequence. If I is smaller than j, then xi must be smaller than xj. Smaller than, so what is smaller than? I guess I should have said that, so let me scribble that down here. So we'll say that for xy in B of H self-adjoint, we'll say x is smaller than y precisely when y minus x is positive. But this is crucial that you want them to be self-adjoint. So usually don't talk about one complex number being smaller than another complex number. Only for real numbers you talk about it. Same way for operators, only for self-adjoint operators you talk about this order. Okay. So in this sense that it is increasing. If y is smaller than j, then xi is less than or equal to xj. Then limit I xi SOT limit exists. Any such monotone limit converges in the strong operator topology. And if we call this limit as x, also x is sup over I of xi in the sense of quadratic forms. That means xi or even lattice theoretic less than or equal to z for all I implies x less than or equal to z. Right? It is a supremum in the sense of a lattice actually. If somebody is bigger than everybody, then it has to be bigger than x. Okay, the proof is very more or less straightforward. For xi and h, look at xi, xi, xi. So what can you say about this? Huh? Tell me everything you can about this.
This is increasing difference.
Huh?
By definition of operator T1 minus T2.
So it is increasing, it is a monotone increasing net and further bounded. Right? There is a bounded increasing net of real number, of positive numbers. And so it must converge. Right? It's convergent. in R plus. You assume that this family is uniformly bounded. That means sup norm xi is finite. By Cauchy-Schwarz, this is bounded by norm xi, norm xi squared, which is bounded by the uniform bond times norm xi squared. Because it's a uniformly bounded. Or just a bounded net of real numbers. So this limit converges. So, but now we proved last time that if you have any quadratic form, it will come from an associated sesquilinear form. Right? So by polarization, identity implies that xi, xi, eta, ini converges for all xi and eta. Right? Because you write this as a combination of linear combination of quadratic forms. And the quadratic form at xi you are saying converges at every vector. So it must converge at x plus psi, x minus I, x plus I xi, x minus I xi. And so you take an appropriate combination of those limits, then you will find the limit of this net. Is this clear? Because this is accessible as a complex linear combination of four things of the form xi, zeta, zeta, and each of those converges. And conversely, that linear combination will also converge. So call this limit converges, and further what can you say? If you take that limit will define a what kind of object? It will.
Depends on the size.
So it will be a bounded sesquilinear form. This limit will define a bounded sesquilinear form. Every such thing must come from a bounded operator. So there must exist a unique bounded operator. Let me just say, so then xi converges to x weak operator upon it. But we want more, we want strong operator convergence. Why is this? You just compute now. You look at norm of xi xi minus xi squared. You just expand it, what you get is how do I know? So I can't find. No, I can't do that. No, I think the way he uses this clever little trick. So it says, he writes this as see, okay. Notice that this X that we manufactured, this is necessarily positive because this quadratic form is positive. And further, we see that X is greater than or equal to Xi for all I. Right? Consequently, X minus Xi is a positive operator. So this I write as norm of Xi minus Xi squared no, let me just take norm y squared. And now this is a positive operator, so you can write this as a z power half times z power half. So less than or equal to norm of Xi minus x power half. No, maybe I should have squared.
First half will be this side and sides. The first part.
No.
Half inside.
Yeah. But they are the same. For a positive operator, the norm power half or power half norm are the same because they are both the spectral radius. Which is just for functions, the soup power half, whether you take the half inside the soup or outside, it is the same thing. Okay, now this is less than or equal to some you already had all the x's bounded by some norm k. Norm x's were all bounded by some k, from which it will follow that x must also be bounded by that k. So norm of xi minus x will be bounded by 2k. Okay, so square root of 2k times xi minus x xi. But then it converges to 0. So any monotone net necessarily converges in the strong operator topology. And it is clear that
So for positive operator, strong operator, limit and weak operator limit same. By
Yeah.
design. For any positive.
if you have a uniformly, otherwise they cannot be convergent. No, you can't have an.
Suppose n times of sigma.
No. It must be monotone.
But here monotonicity is not needed.
No.
Xi minus x is positive.
So we're using x minus x is positive, so
You are using the factor.
so what you're trying to say is that for positive operators, strong operator topology and weak operator topology are the same.
That is problem.
So
Uniformly long limits is
by next class you can come up with a counterexample. Uniform orderliness is certainly needed, but anyway, think about it. Such questions will keep coming up. Okay.
And why not this will the uniform limit of this operator? But there is some counter example, the uniform limit. You said that this is converging SOT.
Yeah.
In more condition, in uniform node, like in the operator node, Ti is minus T, this node means to 0.
Suppose you take a simple example. In L2, let Pn be the projection onto the span of E1 up to En. These are a sequence of projections which clearly increase, and they increase strong operator topology to the identity operator, but they certainly cannot converge in the norm because 1 minus Pn is a projection for every n, and hence has norm 1. It's a non-zero projection and has norm 1. Okay, so to finish this argument, I said this x is also the soup, the sense of form, but that is clear, isn't it? If any z is bigger than equal to all xi, then zi must be greater than equal to xi zi for all zi, but their soup is xi. So xi must be less than equal to z. And so x is less than equal to z. So that this SOT limit of the monotone net is the supremum also in the order theoretic sense. Okay, so this brings us to okay, so and let P of BH for the projections in B of H. I think I've already introduced the notation. These are exactly the operators onto which are orthogonal projections onto closed subspaces. And this is the algebraic reformulation of the geometric fact of being the orthogonal projection. Okay, so there's a little lemma here. Suppose 0 less than equal to x less than equal to 1. And E is a projection. The assertion is then x is less than or equal to E if and only if x equals xe equal to Ex equals Exe. Actually, I don't have to say all this, they follow from just the first condition. Just requiring X equals Xe. If you then take adjoints to this equation, you will get this. And then they say that if X is equal to Xe and you substitute that in this, you will get this. So really it is enough to prove these two are equivalent. Okay, proof. Zero less than equal to x less than equal to 1 implies that by that positivity of the map A going to XA X star, we see that EXE is less than equal to E. Okay, so let me prove those two things are equivalent. So if therefore if x is less than equal to E, then how we're doing this? Yeah. What do I have to do? I want to prove that x equals xe. What does it mean to say that x equals xe? See, x equals xe plus xe perp. Because e plus e perp is 1. So I need to show that xe perp is 0. Right? But what is, if I take any xi in H, let us look at x e perp xi. Now, x is less than equal to e means what? Let me start again. So x is less than equal to e implies x xi less than equal to e xi. But e is a projection, so what is e xi? Norm xi squared. Actually, norm of e xi squared. Norm of e xi squared. Which means went away. So this means that being very clumsy. So this means that x, z is 0 for all z in kernel of V. Which is the range of EPUB, right? That means, but x is positive. So this I can write as norm of x to the half, say, is 0. That is, x is 0. For any xi in kernel of V. But EPUB xi is in the kernel of V. Right? Therefore, if you assume that x is less than or equal to E, x EPUB is 0. That is what you've shown. Therefore, x equals xc. Conversely, if x equals xe, what do I want to say? X equals xc implies x less than or equal to E, I want to say. Right? So this means x and D commute. So I can write x less than or equal to E. Why am I making such a mess here? So x equals xe, then we want to prove that x is less than or equal to E. Yeah, x and E commute, right? So if you take x, therefore x and also x and EPUB commute. So why I'm saying this is, if you write x xi, that will be x is xi. See, basically I want to say that x EPUB is 0. But if I look at just the last term, I can bring the EPUB over to this side, and the EPUB commutes with x, so I can just push it past that. So So I just get x e power xi xi. But under this assumption, x e power is 0. This is actually something I should have just given as a simple exercise rather than going through the whole thing. This means that x e power is 0, and so x xi xi is equal to x e xi e xi. If it is not there, then you just get. So we find that x equals exe. So x equals xe. X equals exe. You just follow from the monotonicity. Please tell me the sensible thing. Because x is less than 1? So x less than equal to 1 implies yeah.
So x is less than equal to e. You started with clear product x xi xi.
So you're saying this implies that x we started with x equals xe. Yeah, so you're saying x xi xi is
just left with x e xi e xi. And that is less than equal to e xi e xi.
In a product is that use projection part is part.
why?
X is less than equal to 1.
Okay. E xi is the same as e xi xi. So x is less than equal to e. Thank you. So I don't know why you said this, but this is just in order to state this, the very obvious consequence that if you take two projections, E and F, projections are also between 0 and 1. Right? So we see that F is less than or equal to E if and only if F equals Fe. And this geometrically this corresponds to range F contained in range E. So the order for projections that comes from positive operators is the same as the order for range inclusion. Consequently, we see that therefore corollary is that if you take the projections in BFH, I want to say this is a complete lattice. What does that mean? That means if you have any collection in place there exists a soup of EA. Because the soup, for projection, the order is the same as range inclusion. So if you have a bunch of projections, that means you have a bunch of subspaces, then one is saying there is the smallest closed subspace which contains all of them. Right? In fact, with a range of soup A equal to union range GI the closed subspace spanned by the union. Union A won't itself be a subspace. You take a bunch of sets, the union won't be a subspace. Like you just take a bunch of lines in R2, the space they span is not the. Anyway, it's sort of the closed subspace, smallest closed subspace containing all the ranges. And that will be the soup, and similarly, there exists an inf A whose range equals and these are all really set theoretic statements, modulo the fact that we only consider closed subspaces, not sets. Okay, so okay, so now we're let me state this as an exercise. If we have two for any n, we do it for any n. So you have projections, then so this is something you should first try to prove for n equals 2 to understand what is happening, and then prove by induction. If you have two projections, what is the support of E plus F. E plus F is not a projection unless they are perpendicular. E plus F is not a projection. E plus F is going to be some positive operator. When you take the support of this positive operator, one is saying that is the same as the soup of E1 and E2. You take two of them. In fact, for two of them, let me say that in fact, for two of them, let me say that in fact, I want to say E1 soup E2. See, we proved all these powerful theorems. We should learn how to use them. So we proved that whenever we have monotone net of uniformly bounded monotone net, it converges, the strong operator topology. I want to say that this is the limit of So what does this mean? I have a sequence of the self-adjoint operator. I'm applying the functional calculus. E1 plus E2 is a positive operator. It has positive spectrum. Now I'm saying you look at the function x going to x power 1 by n. Suppose you write fn x equals x to the 1 over n. Right? So all this is on some the spectrum of this is going to be contained in some compact subset of the positive line. On some compact set, you look at fn x equals x power 1 by n. Then what can you say about this sequence? What happens if fn as n goes large? What for larger is fn monotone? What is the relationship between I'm telling you the wrong thing. So no. Sorry, I looked at the wrong thing. This is also true, but let me give you another problem. Let me write equals limit of This was actually first proved by von Neumann. It says something very nice. What it says is, if you look at this sequence, what are you looking at? You're looking at E1, E2, E1. And then if you square this, what do you get? E1, E2, E1, E2, E1, and so on. In fact, one Neumann said, let's look at the following thing. Let's look at this sequence. E1, E1, E2, E1, E2, E1, E1, E2, E1, E2. Now, why I have put it this way is that every E1, E2, E1 is positive, and they're all contractions. So you have a collection of contractions, so power n is also contraction. So you're saying you look at x power n, look at x power n on 0, 1. So what kind of sequence is that? Huh? For larger n, is it larger or smaller?
Decreasing.
It is monotone decreasing. But nevertheless, the same proof that we gave, that monotone increasing net I gave, the same proof will tell you that a monotone decreasing net, uniformly bounded, must converge, the strong operator topology. So this will also converge in the strong operator topology. And geometrically what this does is, for example, in R2, suppose E1 was a projection onto this. Suppose that is range E2, this is range E1. Then what are you doing? You're taking some point, you're projecting onto this, then projecting onto this, then projecting onto this. In this case, it goes to 0. But in general also, the statement is that this is exactly the, sorry, not so, inf. Even inf E2 is this, and so I should say that, okay, actually even the soup one should be able to but I'm sure this is a correct statement. Except it is not monotone. No, let us look at a lemma we discussed exactly this kind of thing when we apply in a family of functions and we want to apply our monotone limit lemma to a sequence of monotone sequence of functions. Okay, so here is the lemma. So keep it simple. Suppose you have two sequences, Fn and Gn. Are two bounded increasing, that is a monotone sequences of continuous functions okay, on spectrum of x for some self-adjoint x. Fn is an increasing sequence, Gn is an increasing sequence of continuous functions. And suppose such that sup Fn of t less than equal to sup Gn of t. Now the Fn's are all and Gn are continuous functions. So you can apply the functional calculus to x, and then you can have a sequence Fnx of operators, sequence Gnx of operators, and by if f is less than equal to g and f and g are continuous functions, the difference is going to be positive. And positive function of a self-adjoint is going to be a positive operator. So Fnx then sup n Fnx these operators make sense, and these are monotone nets of positive operators because the functional calculus preserves products and adjoints, so f squared will go to a positive operator, and it is clear from the supreme property that in fact this will hold at the operator level. And now this allows us to sure all this is not needed. See, the whole point of the polynomial algebra thing, that you want to study not just continuous functional calculus, but measurable functional calculus. Right? You want to be able to have functions of operators but the functions are not continuous. And the simplest example of a function which is not continuous is an indicator function. So, for example, you take an interval and you write the interval as a see, that's what he said. So, so then you take any number lambda in the real line, and then see, basically you want to look at this function, which is 1 here and 0 here. This characteristic function. And you want to write this as a limit in. Can you write this indicator function of so who is equal to minus infinity to lambda? Yes. Can you find continuous functions Fn which are increasing and whose limit is this thing? So how would you do that? So we want it to be continuous, so you'd want some fn's to look like this perhaps. And for a larger and larger n, we want it to have more and more negative slope. Right? So for example, Fn you can choose to be of t, you can choose to be 1 for t less than equal to lambda minus 1 by n. Zero for t greater than equal to lambda, and in between it will be that linear function, right? Huh? Lambda minus nta.
So that is linear function. ln.
This is what he says. So this gives an increasing sequence of functions like this, which converge to this indicator function. And so by what you know, the sequence of operators Fn of x is for any self-adjoint. The self-adjoint has spectrum in the real line, so I don't care where. For any self-adjoint, for any lambda, I look at these functions and then I take their limit and I have a candidate for. So these guys will increase to indicator minus infinity to lambda of x. See, now I found a way of defining indicator functions of operators. And I guess see, because these FNs are see, I want to say that this thing is actually a projection. I would like to believe it is a projection because indicator functions are idempotents and self-adjoint. But so what is? So I want to use this fact. See what is true about Fn? Fn is between 0 and 1 for all n. Right? So observe that Fn squared will be less than or equal to Fn. Actually, I don't even have to do that. We have proved before. Fnx is a sequence of operators in the unit ball. And on norm-bounded sets, we had verified that multiplication is jointly continuous. So if Fnx converges strongly to this indicator function of x, then Fn squared should also converge to that indicator squared. No, that still requires a little. Okay, so why is this a projection? So kind of. I have. Okay, so I guess we should be a little careful. So these Fn's actually depend on a parameter, on the lambda. Let us call these functions Fn lambda. Then we know that they increase to some operator which we choose to call 1 in minus infinity lambda of x. Now before doing this, I must justify various things. I could have done this by choosing any other sequence of functions which increased. Right? I need to have chosen this particular linear approximation. I could have chosen some other family of functions which increase the indicator function. So I must show that no matter what family of functions I have which increase to this thing, they will converge to this same one fixed operator. I must justify calling this operator. I must prove that this thing is a projection depending only on lambda and x and not on the way that I chose the approximating sequence. So he. Okay, so this is the way he. So I think This part I hadn't really prepared for. I didn't think we'll get this far. So let's do this next time. And yeah.